Let's let f arrow be the following vector field. So we'll have here z comma z comma xy squared. Let's define capital S to be the cylinder. X squared plus y squared is equal to 9 for negative 4 less than or equal to z less than or equal to 5. And then let's find the integral over the surface of the curl of f dot ds arrow. Now, even the fact that it says curl of f here instead of just a plain f probably suggests that we ought to be using Stokes' theorem. Now, let's actually just draw a picture of the surface itself. Yeah, so there's this cylinder. It's just many stacked copies of a circle of radius 3. So we've got, okay, circle of radius 3 here, and then circle radius 3 above, and so on, right? Like, oh, and it stops with z equal to 5, 5 there, and it goes on below until z equals negative 4. Okay, so that's where, forgive me, I'll try to continue the z axis there. There's, I don't know, I didn't give myself much room to label this. So there's two boundary pieces to this surface, right? Think of this like a finished off paper towel tube, and there are two circles that serve as boundary. Now, is this one of these problems where we use Stokes' theorem twice, once in one direction and once in the other? Probably not. Let's not get carried away. Yeah. So if the problem lends itself to that and it's natural, great. But I think that's the point here is for this surface S, S is probably the nicest surface. S itself is probably the nicest surface whose boundary is the two red circles, right? The red circle above and the red circle below. Okay, so let's think about um, only using Stokes' theorem once. Basically, converting this integral um, into a line integral and just doing the line integral instead of trying to find another surface because there's probably just not a nicer surface. I mean there's yeah for this two circles. Think of are there other surfaces whose boundary consists of these two circles? Certainly, you could take like a globe, right? Take a sphere and chop the top and bottom, sort of like an orange, but like in two chops. But like I don't think that that's going to be really much nicer to work with. So let's think about orienting this thing outwards. So sorry, maybe I'll use a new color here. But if we were to orient outwards like this, then you'd have your orientation arrow, curly, things like that. And so then as far as this circle goes, we have to orient that way, which I guess from above looks clockwise. And then here, we'd have to orient counterclockwise. Maybe it helps if I take one of these circular thingies and draw. Um, this is meant to be the in front. Okay, so yeah, some of these are a bit hard to draw, I guess. Yeah, so let's clarify this by saying that the boundary of S consists of two circles. So let's call it C upper and C lower. And the upper circle is oriented like this, okay, that way. And then that would mean the lower circle has to be oriented like that. So if we were to do some parameterizations here, so for C upper, we could have R of t equaling, okay, so notice this is, viewed from above, it is actually the unusual direction in that it's clockwise. So we'll have to do something like 3 cosine of t, comma, and then negative 3 sine of t. Z coordinate is just 5, a constant the whole time. And here t goes from 0 to 2 pi, since we want the whole circle. For C lower, a parameterization written as a vector function could be 3 cosine of t, comma 3 sine of t, so no minus signs because the circle here is oriented the direction that we normally want to go. So looking from above, this is in front, yeah? So we go that way, and then this is the part that's behind, and it should have been shaded. I'll try to maybe redraw this a little better just by having, without the axes in the way. So the point is that if we lightly draw in, okay, this is still in front, yeah? Then we've got traveling around this way, and then here, this is this bottom edge that I'm highlighting is the front of this can, of this cylinder. So orient, oh my goodness, something's, let's see. Oh, sorry, I'm getting myself confused. Let me try this again. Let me just hit undo a couple times. I drew the arrow and I didn't follow the direction so this arrow here, right? So just that piece needs to follow in the arrowhead needs to point the same direction. Okay, so we go this way. Yeah, like that. And then here, the arrowheads go that way. And then we'll do this part dotted there as well. Okay, there we go. So then, oh yeah, to finish off the parameterization for the lower circle, z coordinate's just a constant -4 there. And then again, here we go from 0 to 2 pi for t. So we have two different parameterizations for the two separate circles. That makes sense. And so then the double integral over the given surface of the curl of the vector field dot ds is, according to Stokes' theorem, the line integral over the boundary of the surface oriented in a compatible way of the vector field itself, not the curl anymore, just the vector field itself, f dot dr. But the way that this boundary works out is this boundary consists of two pieces, this one and that one. So what we really have is we're just going to have two separate line integrals. So the line integral c upper f dot dr, and then the line integral over c lower of f dot dr. So let's work out those two integrals. So what's the first of these integrals here, right, is going to be written as an integral in t, 0 to 2 integral 0 to 2 pi of, well, okay, we need the vector field itself, which, let's go up here. It was z comma xy squared, but we need to make use of the fact that the upper parameterization looks like that. So every z needs to get replaced with a 5, right? So 5 comma 5 comma x times and then, yeah, 5 comma 5 comma, and then x times y squared. So, well, 3 cosine of t times -3 sine t quantity squared. And then that needs to get dotted with the derivative of r, right? So r prime, let's just stare at this and compute r prime in our heads, and we'll have -3 sine t comma then the negative sign here is just being copied here. Then 3 sine t differentiates to 3 cosine of t, and then the 5 differentiates to 0. Okay, dt. So that's this integral. Now we need to add to that the next integral. So the next integral should be plus 0 to 2 pi of, again we need f, but we have to compose f with a new r, right? So now we look at this r, f is still zz xy squared, so we'll now have -4 comma -4 comma, okay, xy squared. So x is 3 cosine t, and y squared is still now y is now positive 3 sine t quantity squared. I know this is a little funky. You might say, look, the square is going to get rid of the minus sign here anyway, so why not write the same? But I just want to be very, what's the word? I want to be very consistent with what's going on. So the minus sign here is because of the minus sign there, yeah? And then we need here r prime. So we look at this r and we take a derivative. So 3 cosine of t differentiates to -3 sine of t. Ooh, let's write that better. And then 3 sine t there differentiates to 3 cosine of t. And then -4, the constant, differentiates to 0 dt. You can work out some of the details here, but what's nice is that when you perform these dot products, take a look. 0 times the more complicated thing, yeah? So actually, this integral, we could also just come, now imagine, other than performing the dot product, imagine giving this integral to somebody. So we could actually combine, like somebody in Calc 1, we could all combine this into one t integral. Like, it doesn't make sense to do it any before this, but now we'll have 5 times negative 3 sine t. So we'll have, negative 15 sine t minus, oh, so then, sorry, this 5 times this negative 3 cosine t, that's why I said minus, so minus 15 cosine t. And then, well, the next term that we should tack on is 0 times whatever, but, well, that's 0 times whatever, so let's not. Then let's perform this dot product and put the result here. So we'll have positive 12 sine t, and then, oh, not comma, ooh, we're doing dot product. And then negative 4 times 3 cosine t is, we're going to tack on a plus negative 12 cosine t there. Okay, and then we won't go through this integral. It's really not bad. Fun story. In the end, you get just the number 0. You just get the scalar 0. There's a lot of work to get a 0 here at the end, but at least we're demonstrating some of the process. And I think the point of this final question amongst the set of sample problems we're looking at is to say, don't go overboard all the time. You don't always use Stokes' theorem twice. Sometimes you should just use Stokes' theorem once. Sometimes you should just use Stokes' theorem not at all.